In the previous lecture, we have discussed the concept of central force. Actually, we have only defined the central force and explained the definition by taking two important examples of gravitational force and electrostatic force as a central force. Now, we are going to start to discuss the important properties of central force fields. Actually, we will discuss almost 5 important properties of central force field, and in this lecture I am just going to deal with the 2 important properties. The remaining properties will be dealt in the forthcoming lecture. So let us start to know what are the important properties of central force fields. The first property which we mention here is that the angular momentum of a particle moving in a central force field remains conserved. That is, it is constant. It means whenever a particle will move in a central force field, its angular momentum will remain constant. As angular momentum is a vector, you know, so if angular momentum is constant, that means its magnitude and direction both will be constant. This is actually a very important property, and this fact is invariably used in developing the theory of central force field. So remember it, that angular momentum of any particle moving in a central force field will never change in magnitude and in direction. It will always remain constant. And the another important property which I have mentioned earlier, that actually I have told you from the beginning, that whenever a particle moves in under a central force field, definitely the motion of the particle takes place in a plane. So we simply say that motion under a central force field is contained in a plane. And so I have mentioned here that the path or the orbit of a particle moving in a central force field is a plane curve. That is, the particle moves in a plane. So these are the two important properties of central force field, but as I have told you, these are not only the two, these are not the properties of central forces only, but we will deal with the other important properties in the forthcoming lecture. In this lecture, I am going to explain only these two properties. Okay? So if you want to know the properties of central forces in detail, you have to watch all the videos based on properties of central force field. So I have marked here that this is properties of central force field 1. It means in this first lecture we will only deal with these two important properties. So what are the two important properties? Can you say? The first property, in short, you can say that during motion of a particle in a central force field, the angular momentum of the particle remains constant. And the another property is what? That is, the motion under a central force field is a motion in a plane. That it means particle always moves in a plane if it is moving under a central force field. Now, one by one, we will explain these two important properties of the central force. And for the explanation of conservation of angular momentum, let us see this figure. Actually, I have shown here that there is a particle, let us say of mass m, moving and it is at any time t located at this point P. Okay? And the motion of this particle is actually under a central force field. Let us say F is the central force which I have marked here, and under this central force F the particle is moving. Okay? And you can see the figure, this point O is actually the center of the force, that is center of the central force. I have taken this point O. Now you can see that any moment t, the position vector of this particle P with respect to the center of force O I have marked by this vector r. So r is the position vector or the radius vector of the particle at any moment with respect to the point O, which is actually the center of force. O is what? O is the center of force. Okay. Now, in the direction of this radius vector r, you take the radial unit vector r hat. So I have marked here r hat. This is actually the radial unit vector which is directed along the vector r. Okay. Now, to prove the angular moment, conservation of angular momentum of this particle in this central force field, let us think about how angular momentum is defined. Actually, here we will define the angular momentum in two ways. First of all, we will define it by the Newton's second law of motion. You know, Newton's second law of motion in case of translatory motion is what? That force acting on a particle is given by dp by dt, that is rate of change in momentum. Similarly, in case of rotational motion, when you talk about the momentum, where there we define actually the angular momentum, which is actually the rotational equivalent of linear momentum. And at the place of force, we define torque. Okay. And so, according to Newton's second law of motion, if you want to define the torque acting on this particle, torque means moment of force. So, you can say, consider a particle of mass m moving in a central force field. Okay, and F is the central force. F is the central force acting on this particle. Acting on it. O is the center of the force. Okay. So, you know that how a central force is symbolically represented. You know, if F is the central force, then it is represented by F of r times r hat. You know, and this F of r may be positive or it may be negative. Okay. Now, we will define the torque acting on this particle due to this force. So, torque means moment of force. Torque, or you can say moment of force. Moment of F about O, that is the center of force. How this torque is defined? You know, this torque is defined as tau equal to r cross F. This is just the basic definition of torque. You know, you have definitely studied this definition of torque in your study of rotational mechanics in lower classes. So, if tau is the torque acting on this particle, then it is defined as r cross F. Now, let us put the value of F. You know, this F, as I have defined here, and you have learnt it in the previous lecture, this will be F of r times r hat. Okay, and you can write it, since F of r is a scalar, so you can write it r cross r hat. But r hat is a unit vector directed along the radius vector r. So you know this r hat is simply equal to r over r. Okay. So and this will be equal to 0. Why? Because you know r cross r, this is equal to 0. Cross product of two same vectors is always 0, you know. So definitely you can say that if a particle is moving in a central force field and we find the torque acting on the particle about the center of central force, then definitely that torque will be 0. It is always 0. Okay. Now you can also define this torque by using the Newton's second law of motion. So by second law of motion, how this torque will be defined? You know, torque is defined simply as the time derivative of angular momentum. If you denote the angular momentum by the vector j, then torque is equal to dj by dt. This is just analogous to F is equal to dp dt, where p is linear momentum and F is force. And you know, in fact, this torque tau is just a rotational equivalent of force F, and the angular momentum j is the rotational equivalent of linear momentum p. Okay. So j is what here? J is angular momentum of the particle. This is angular momentum of the particle. Okay. So this equation has been written on the basis of Newton's second law of motion, okay, for the rotational motion. Now you can compare equation 1 and equation 2. What you observe here? According to equation 1, the torque acting on the particle moving under the central force field is always 0. This tau is equal to 0. And Newton's second law says that torque acting on the particle is simply the time derivative of angular momentum j. So you can equate these two equations, and so you can write from equation 1 and 2 that dj dt is equal to 0. Okay, dj dt equal to 0. And if dj dt is 0, you can say what will be j? Definitely j will be equal to a constant, because derivative of constant is 0. So we can easily see here that during the motion of a particle under a central force field, the angular momentum j of the particle remains conserved. So, and since j is a vector and you say that j is constant, it means both the magnitude and the direction of j remains constant. Okay, so both magnitude and direction of j means angular momentum, remain constant. So you can see how easily we have explained or we have proved the first property, that the angular momentum of a particle remains conserved during its motion under a central force field. Okay. Now we will prove easily in the same way the second property which I have mentioned, that motion under a central force field takes place in a plane. So motion in a central force field takes place in a plane. Always. This motion is always in a plane. Takes place in a plane. Okay. Now we can also prove this fact very easily by using the above fact. Just you have seen that the torque tau is equal to 0 in a central force field. Central force field, torque tau, which is actually defined as R cross F. But as F is a central force, so you can write that this F is simply equal to F of R times R hat. And just you have seen that this product becomes 0. Okay. That is, you can say that during the motion under a central force field, the vector product of the radius vector R and the central force F, this will be always equal to 0. Okay. Now you know from the Newton's second law of motion that this force vector F will be defined by m times a, where a is actually acceleration of the particle. Okay. And as you know, acceleration is defined by simply the time derivative of velocity. So instead of a, you may write dv dt. Okay. So F is equal to dv dt. Okay. Now we can put this expression for F, that is m dv dt, at the place of F in this equation. So let us put it here. So you can see that therefore R cross F, but instead of F now we will write m dv dt, and this will be equal to 0. Okay. Now m is a scalar, positive scalar, so you may write this LHS of this equation in this way. This is m times R cross dv dt equal to 0. Now, as m is mass of the particle, and you know in classical physics, mass of a particle is never 0. Whenever you talk about a particle in classical mechanics or Newtonian mechanics, definitely the particle has mass. So m is not 0, but the product of these two quantities is 0. So definitely the second factor will be 0. Okay. This will be 0. So you can see that we can write that R cross dv dt is equal to 0. Why? You can say because m is not equal to 0. Now we can write this expression in this way. This may be written as d dt R cross v. How you can write this expression as d dt R cross v? You can understand it. See here. In fact, if you evaluate d dt R cross v, then by the rule of differentiation of product of two vectors, you can see this will be dr dt cross v plus R cross dv by dt. Okay. Now you know that dr by dt is what? This is actually velocity of the particle v. So this is simply v cross v plus R cross dv by dt. Okay, r cross d by dt. But you know that this v cross v will be 0. So this is 0 plus r cross dv dt. Okay, r cross dv dt, because v cross v is 0. And so this is equal to simply r cross dv by dt. So you can see I have proved that this d dt r cross v is equal to r cross dv dt. So I have written here, instead of r cross dv dt, d dt r cross v. Okay, have you understand or not? So this result may be written like this. Okay, now as this d dt r cross v is 0. So now let us integrate it. So you can see the integral of differential of r cross v. Differential of r cross v. What will be this? This will be integral of 0 dt. Okay. Now you know that integral of differential of r cross v. This will be what? This will be simply r cross v. Have you understand or not? Since integral and differential both are actually the operators of just opposite manners. So this integral actually cancels the differential operator, because you know that integral of dx is equal to x, integral of dy is equal to y, and so at the place of x and y here there is r cross v. So you can say that integral of this differential of r cross v is equal to r cross v. Okay, and this will be what? This is 0 plus some constant. Here the constant we write by the symbol h. This is just vector h, because LHS is vector, so definitely that should be vector. This h is what? This is integration constant. This is integration constant. Okay, and so r cross v is just a constant, and that constant I have denoted by the symbol h. Actually we will see that actually this h is nothing, it is simply the angular momentum per unit mass. We will later recognize it in this way. Say this is your equation 1. Okay, so r cross v is equal to h, and where h is actually a constant vector. Okay, now let us multiply this equation 1 both sides by r dot. So multiplying both sides of equation, what is equation number? That is equation 1. Equation 1 by r dot. It means we take the dot product or a scalar product of this equation 1 by r. Okay, so you can see what will be your result. This will be r dot r cross v, because in LHS there was r cross v, so this will be r dot r cross v, and in RHS there is h, so this will be r dot h. But you have studied the scalar product, triple scalar product, and from the properties of triple scalar product you can say that this expression r dot r cross v can be written as r cross r dot v. This can be written like this from the properties of triple scalar product, and this will be equal to r dot h, r dot h. Okay, but can you say what is this r cross r? Definitely you can say this will be simply 0. So this LHS is 0 actually. So 0 is equal to r dot h. Okay, that is, you can say that r dot h is equal to 0. Say this is equation 2. H is where actually a constant vector. Okay, now since the scalar product of these two vectors r and h is 0, so you know that the angle between these two vectors will be 90 degree. Okay, it means the vector r is perpendicular to the constant vector h, and so since r is perpendicular to the constant vector h, so definitely the motion will take place in a plane. Okay, r is, you can give this argument that thus r is perpendicular to h always, and h is a constant vector. So the motion takes place in a plane. That's why we say that motion under a central force field always takes place in a plane. Okay, so you can see that how easily we can prove that motion under a central force field takes place in a plane. Again, as I have told you earlier, that this vector h, which I have assumed here, this is actually equal to what? H is at the place of r cross v. So now let us recognize what is this vector r. Now this is just an extra fact which you have to remember. You can see r cross h, this is equal to, sorry, r cross v, not h, r cross v, this is equal to h. I have just shown earlier. You can see this equation. R cross v is equal to h. Okay. Now let us multiply this equation both sides by m. So m times r cross v, this is equal to mh. This is mh. Okay. And what will be this? This can be written as r cross mv, and this is equal to mh. And you know that this mv is linear momentum of the particle. So this is r cross p, and this equal to mh. Okay, r cross p, and this is equal to mh. But you know that this p is linear momentum, and r cross p, which is actually called the moment of linear momentum, and moment of linear momentum is nothing, it is simply the angular momentum. So this r cross p is what? This r cross p is angular momentum of the particle. So you can say that this angular momentum J is equal to m times h. Okay, this is also an important result, and from here you can see what is this h. H is equal to j over m. So you can say that h is also angular momentum vector, but it is angular momentum of unit mass. So you can say this is angular momentum per unit mass. Per unit mass. Okay. Angular momentum per unit mass. Okay. And actually this angular momentum can be expressed also in terms of the polar coordinates r and theta. These things I am just going to discuss some extra point. What the property was to prove, or that has been already proved, but I am going to deal with some of the important results which will be invariably used in the forthcoming lectures. So now you can see that this J is equal to what? This is mh. Okay, this is mh, and h, as you have seen that this has been defined by r cross v. Okay, this is r cross v, and as you know that the motion in a central force field takes place in a plane which you have just proved. So you can see that this velocity vector v in a plane can be written as, this is Vr times r hat plus V theta times theta hat. We have just seen in the earlier lecture that in a plane, in plane polar coordinate, velocity has two components, radial component Vr and transverse component V theta. And the radial unit vector is r hat and transverse unit vector is theta hat. So what will be this result? Now take the vector product of these two terms with this r. So what will be the result? This will be Vr times r cross r hat, okay, and plus V theta r times r cross theta hat, r cross theta hat. Okay. Now see, r cross r hat, since these two vectors are in same direction, so this will be simply 0. So this will be m 0 plus v theta. Now if you consider that this r cross theta hat is equal to a unit vector n hat, then this unit vector will be actually perpendicular to the plane of r, perpendicular to the r theta plane. If you consider that plane xy plane, then this n hat will be in the direction of z axis. Okay. If you consider that the plane is xy, then this n hat will be k hat. Okay. But I have not considered here particular plane, so I have written here that this n hat is a unit vector perpendicular to r theta plane. Okay, r theta plane. So this will be m, sorry, here there is also in fact r. So this will be, in fact you should write it in this way. I have just mistaken here. You can see this term should be written like this. You can see. In fact, this is v theta, and this r vector can be written as r times r hat across theta hat. Now the cross product of unit vector r hat and theta hat, that is equal to in fact n hat. So this will be now what? This is m into r into v theta into n hat. Okay, n hat. Okay. Now what is the expression for v theta? You have studied in the previous lectures that v theta is equal to r theta dot. Have you studied or not? Remember, I have dealt with the velocity and acceleration in the previous lecture. So you can remember that this transverse component of velocity v theta is given by r theta dot. So finally we get that the angular momentum vector of a particle moving in a plane is equal to what? This is mr square theta dot times n hat. Okay, and if you want to write only the magnitude of this vector j, then this will be simply mr square theta dot. This form of expression for angular momentum is very important, and you will see the use of this expression in our forthcoming lectures will be in fact very frequently. Okay, and so can you say what will be now h? H, as you have seen, this is j by m, so this h will be simply equal to r square theta dot. Okay, r square theta dot. So these were some of the important results, but I have done these things some extra because we have only to explain that the motion under a central force field takes place in a plane, and that fact was actually proved here. But I have discussed some more extra results which will be invariably used in our forthcoming lectures. So I hope you have understand these two important properties of the central force, and as I have told you earlier that we will actually deal with the 5 important properties of central force field, and in the forthcoming lecture you will see the other properties, how what are those properties and how they are explained, we will see in the forthcoming lecture. So definitely you should watch all the videos on the properties of central forces, only then this concept will be clear to you.